Hello, my name is Victor Korja, and the paper I will be describing today is titled Deep Neural Networks for No Reference and Full Reference Image Quality Assessment by several researchers at the Department of Video Coding and Analytics in Berlin. The focus of the paper is on an implementation of a convolutional neural network for image quality analysis. As you can probably tell from the title, the paper's contents are related to image quality assessment, an aspect of media that deals with assessing the perceived quality of digital images. The need for this field can be demonstrated by the simple example of image communication. When a person sends a digital image to someone else, that image undergoes a series of procedures designed to optimize the efficiency of the communication, such as digitization, compression, and transmission, all of which can cause potentially visible distortions. Research into image quality assessment can help provide resources that lead to justifiable evaluation and optimization in such communication systems, such that future communications contain fewer or less noticeable distortions. Image quality measures, or IQMs, are generally classified into three categories based on how much information is available about the image's original state. If there exists a complete copy of the original, the IQM is described as full reference. Alternately, a no reference IQM would make use only of the distorted image, without any information about the original. The third category are reduced reference images, where only some features about the original image are available during the measurement process. It is clear that from full reference to no reference approach, the computation difficulty greatly increases, since no original data can be exploited for comparative analysis, which is unfortunate since having no original to refer to is a situation which occurs much more frequently than the alternative. However, there are some situations where using no reference image analysis is simply unfeasible, such as for video analysis, due to the incredibly large level and variability of noise and distortion. You could still use it for video analysis, but image reconstruction would be a lot more difficult for no reference approach than it is for a full reference approach. The generic approach to image quality assessment uses models of a human visual system, or HVS, as well as statistics derived from natural images, and attempts to determine image distortions by simulating the HVS. For no reference assessments, an additional model is used, which contains information about statistical regularities of natural images. A newer approach to image quality assessment relies only on the data available in a dataset, without a preference for specific models, which allows the implementation to be much more dynamic. Additionally, a relatively novel practice is to combine the IQMs obtained from algorithms with models of saliency. Saliency is the noticeability of a certain entity or feature, and in this particular application would be used to determine the significance of a distortion depending on its placement within an image and the likelihood of its observation by a human viewer. For example, given the picture on the screen, the effect of a distortion would be much more noticeable when focusing on the castle rather than the background, especially considering that such distortions are as underexposure or compression loss. This is supported by the fact that human visual perception is not nearly accurate enough to see all distortions, even when looking directly at them, so saliency models can also take into account the visibility likelihood given the context of the surrounding portions of the image. This is also caused by the fact that the human eye naturally gravitates to certain areas, colors, shapes, and effects in an image, all of which can be accounted for in a model. The approach proposed in this paper falls under the newer category, which uses only the available data, and utilizes a deep convolutional neural network, or CNN, for the image quality assessment. The benefit of a CNN for image analysis is that the machine learning aspect can be employed within every portion of the process, including both the feature design and extraction, the algorithm design, and the regression model. Additionally, convolutional neural networks have been shown to outperform alternative implementations that separate the feature identification and algorithm design steps. This paper proposes a specific CNN architecture, including 10 convolutional layers, 5 pooling layers to perform feature extraction, and 2 layers which are fully connected, meaning they connect every input from a previous layer to the next. This architecture is based on the actual structure of a primate's visual cortex, and is both sufficiently deep to outperform existing models and shallow enough to prevent resource limitation from being an issue. Another consideration the authors had was the lack of available data on which they could train and test their model, since full reference analysis requires high-quality image annotations. To overcome this, the authors extracted small patches taken randomly from images within such existing datasets and assigned them quality labels based on the features of the same patch in the original image. This also increased the model's functionality, as it allowed it to be trained to consider luminance and contrast distortions, since these features are more easily seen from an extracted patch of an image than in the image as a whole. Based on this approach of breaking an image down into patches, the authors proposed two methods of determining an image quality assessment. The first, named Deep Image Quality Measure for Full Reference IQA, or DIQAM-FR, obtains the IQM simply by averaging the quality measures of each patch with nearby patches, and obtaining that average for successfully greater areas of the image. The second method, titled Weighted Average Deep Image Quality Measure for FRIQA, uses a similar approach, but rather than a simple average, it first applies a relative weight to each patch based on the significance of that patch's quality on the global image quality. Going a bit more in depth as to the author's approach, the full reference implementation begins with a Siamese network, which are commonly used in situations where a similarity index needs to be calculated. Once the features of both the original and the distorted image are extracted, they are fused together and entered into a regression model. The entire model on the screen is run multiple times over. In this experiment, the authors had a 14-layer approach to account for small patch sizes of 32 by 32, and upon the completion of all feature extraction processes for an image with an initial size of 224 by 224, there are about 5.2 million parameters which can be used to train the model, which are extracted through the feature extraction step. The same two methods can be used for no reference IQA by removing one of the feature extraction processes and basing the entire measurement on the given image and known statistical models. As mentioned previously, the authors employed two distinct methods of determining a global visual quality from a collection of small local visual quality measurements. The first method, which uses simple averaging, uses the equation on screen. Q, representing the global quality estimate, is set equivalent to the sum of all local visual estimates, y, divided by the number of patches, n sub p. An extension to this equation calculates the quality loss by using mean absolute error, the sum of differences between a local patch's quality and the perceived global quality, divided by the number of patches. The second method, weighted average patch aggregation, takes into account the differences in the relevance of each sampled patch. As described before, a patch sampled in the middle of a neutral background will be far less discernible than one in the middle of the image's natural focal point. The method determines a value alpha sub I for each patch, which holds the weight of that patch as a measure of its visual relevance. The global quality estimate Q, in that case, is equal to the sum of the product of the normalized weight P and the local perceived quality Y for all the patches sampled. The rightmost part of the left equation shows that this can also be written as the quotient of the sum of products of all local weights and qualities and the sum of all weights. The loss function for this method is simpler to calculate. Since the saliency model takes into account perceptual loss, the global loss is simply the global quality estimate Q minus the global perceived quality Q sub T. For the training and testing of their models, the authors chose 4 datasets composed of both quality annotated images and images taken under real-life, non-studio conditions. The first database, LIVE, contained 779 annotated images. These were not all distinct images, but rather they were a set of 29 reference images that were distorted using a specific distortion type at a specific distortion level. What this means is that each image was subjected to either JP2K compression, JPEG compression, additive white Gaussian noise, Gaussian blur, or a fast-fading Rayleigh channel, each time at a different level of distortion. In order to provide a baseline quality rating, people were asked to provide a rating based on looking at one specific image at a time. and the results were all compiled using a model to provide the best quality estimate. The two other datasets containing annotated images were the TID 2013 database, with 3,000 images based on 25 reference images, distorted using 24 distortion types at 5 levels of distortion each, and the CISQ database, with 866 total annotated images, based on 30 reference images, with 6 distortion types at various levels. The rating procedures varied somewhat for these databases, but provided the same end result of a quality baseline. The final dataset used was the Live in the Wild Image Quality Challenge database, also known as CLIVE, containing 1,162 images taken under real-life conditions with varying objects, scenes, luminance conditions, cameras, and leading to a large variety of distortions and impairments, such as over and underexposure, blur, grain, and compression. Since the images obtained were not professionally created, they could not be used for full reference analysis due to inherent distortions, and this database was therefore used for the no-reference model. The quality ratings were obtained by a mean opinion score from a crowdsourced online study. In order to test a variety of scenarios with their models, the authors trained and tested their models on individual datasets, then trained them on one dataset and tested them on another to determine the method's generalization. For each dataset, the data was split into training, validation, and test categories, and the quality ratings were all mapped to have the same scale, to make a cross-dataset evaluation more accurate. The author's method's prediction accuracy for the image quality was evaluated using the Pearson Linear Correlation Coefficient, or LCC, and the Spearman Rank Order Coefficient, or SROCC, and they were used for prediction monotonicity or consistency. The results of the performance evaluation were relatively diverse, but largely demonstrated the superiority of the author's proposed methods over the current existing state-of-the-art models. On the image of the results, I have outlined the models proposed by the authors, and highlighted the result of each time when the proposed model was the best in its category, which happened quite a few times. For full reference image quality assessment, one of the two models is the best in every category, except the SROCC evaluation on the live database. However, the benefit of using weighted average patch aggregation can clearly be seen, as it outperforms the simple average method in all tests. The opposite is true for no reference analysis. While the methods are largely superior to others, the simple average method outperforms the weighted one in all cases. Looking at the performance comparison for distinct subsets of the TID 2013 database and the CLIVE database, the authors approached for no reference analysis are consistently in the top 3 spots, although they are outperformed noticeably by the FRIQEE model on the CLIVE database. Another analysis performed by the authors tested only their models with 4 distinct distortion types from the TID 2013 database: Gaussian blur, JPEG compression, JPTK compression, and local blockwise distortions of different intensity, abbreviated as LBDDI. The results provided some insight as to the differences in effectiveness of the two models over the previous tests. For full reference analysis, the weighted average performed better in all instances, demonstrating the significance of incorporation of a saliency model into image quality assessment. For no reference analysis, on the other hand, the simple average method performed better on the first 3 distortion types, but worse on the last. Since the first 3 distortion types didn't have characteristics which would be well suited to aggregation approaches, while the fourth one had a multitude of small, distinct distortions, this led to the conclusion that the weighted average method is mostly suitable for no reference analysis when the image distortions and scenes are inhomogeneous or have many disparate elements. On screen before you is a set of images obtained during one of the author's experiments. The original image, at the top of the slide, has some distortion between the foreground and background elements, and was assigned a quality score of 34 by the mean opinion score of an online survey. Below that, the 4 images, from left to right, show the distortion models of full reference analysis with simple and weighted average, and no reference analysis with simple and weighted average. The blue colors indicate a low level of distortion, while yellow indicates a high level of distortion. In the bottommost 2 images, you can see the weights assigned by the saliency model to portions of the image by the full reference model and the no reference model. where blue represents low and yellow represents high saliency, or significance. As you can see, the full reference saliency model was much more effective at determining areas of significance, and based on the scores listed under each of the model's outputs, you can see that the full reference scores were closer to the known image quality, while the weighted no reference model had the lowest accuracy. In this experiment, the authors implemented an image distorted with LBDDI. Those are the blocks you can see throughout the image. This particular distortion type allowed the authors to test the local quality and weight maps for an image with very distinct and spaced out distortions. The disparity between the distortions and the image itself allows the weighted average model to assign higher weights to the distorted regions, considering how much they stand out, and therefore better predict an area of distortion than the model which uses simple averaging. Here are the model outputs for this particular image. On this occasion, as expected based on prior conclusions, the weighted average models performed much better than the simple averages, while the full and no reference models both have a similar output from the saliency model. For the third demonstration, the authors showed the contrast of the model's effectiveness for one image with quite a lot of underexposure, and another where there is a clear contrast between areas of high importance and the background due to the darkness. As you can see, the model's performance is much better in all cases for the right image, especially the saliency model, which pretty accurately demonstrates the areas of relevance in the image. In an attempt to determine the generalization capability of their model, or its applicability on a test set separate from the training set, the authors trained their model with data from one database, in the first case, Live or TID 2013, in the second case on Live only, and in the third case on TID 2013 only, and then tested it on a different database, in the first case on CSIQ, Live or TID 2013, in the second case on CSIQ or TID 2013, and in the third case on CSIQ alone. As shown in the first table, the weighted average model demonstrated a very high, and half the time the highest, performance in a full reference test, while the simple average database had quite a low performance. The second table shows the same experiment with no reference images, where once again the proposed models had a good performance on the full dataset. While the performance was not quite as good on subsets of the test database, this was accounted for by the fact that the test database had distortion types not present or learned in the training set. The third table, with one more set of training and test databases, showed that while the proposed models can outperform existing models, they are far from perfect, since even with the highest scores of 0.717 and 0.733, they are far from the optimal score of 1. The final portions of the author's research dealt with justifying the selections they had made for certain variables in their design. The first variable was the number of patches to sample per image, which in all the prior described experiments was 32. As you can see on screen, in these 4 graphs, showing the model performance given a variety of different input sizes along the x-axis, both the simple and weighted average models, for both full and no reference analyses, reach or very closely approach their absolute maximum values around an input of 2 to the 5th, or 32, patches. The next justification provided was for the amount of time each model was allowed to run. The authors set this at a constant 3000 epochs, where one epoch was the time required for one sample image from the training set to be used once, without any data reuse. Once again, the value of 3000 was chosen due to an approach to the absolute minimum of all 3 types of modeling in terms of the data loss through analysis. While several other justifications were also provided, they were largely based on previously stated information, such as the dimensionality and depth of the neural network, or the number of features extracted from the image. One more justification specified by the authors was for the depth selected for the neural network. With the implemented network having a depth of 17 layers, the authors performed an experiment to remove several layers, and even reduced the feature vector dimensionality from 512 to 256, thereby cutting in half the number of parameters considered by the model. The final model output considered 790,000 parameters, rather than the original 5.2 million, but achieved similar performance levels to the original. As shown in the table on the slide, there was a marginal difference in the performance measure on the Live and TID 2013 databases, and a slightly larger, yet still relatively small difference on the CSIQ database. The authors explained that their choices for the original architecture were based on available resources, but that increasing the depth and complexity of the network would lead to increases in its accuracy. However, when they considered the immense increase in computational cost and the marginal improvement in accuracy, they felt that the selected architecture was near optimal. To review the author's overall work, the paper presented two novel neural network architectures for image quality analysis using feature learning and regression, one with simple averaging of random patch quality, and the other through weighted averages, and accounting for both full reference and no reference image quality analysis. The proposed approaches are purely data-driven, meaning they do not rely on custom selection of features for extraction, prior knowledge of the human visual system, or image statistics, and are dynamic in their selection of learning parameters. The experimental results demonstrated the model's superiority in multiple areas compared to current state-of-the-art models, yet also demonstrated areas of growth for the future, as well as some limitations that were discovered during the research process. Some limitations of this work were that there is not a large number of large and diverse databases available with quality annotated images, and that there is not yet a perfect method of determining image quality to use for reference beyond psychophysiological assessments, such as mean opinion scores in online surveys. Another limitation was that the authors optimized their model based on mean absolute error, or the difference between the global perceived quality and the global quality estimate, which may not be the most efficient method of optimization. Finally, the authors stated that their model still had definitive room for growth in terms of determining the optimal feature parameters to extract from an image, and the ratios between various parameters in analysis. The authors also proposed some areas for future work, including the implementation of the model for the third area of image assessment, reduced reference analysis. This was described theoretically in the paper, but not fully implemented in the model. Additionally, an improved saliency model, which would be capable of ignoring the structural elements of an image, as well as the type and distribution of the distortion, would be very helpful in assigning weights to different patches. The authors proposed several extensions to their model, including the addition of an explanation method to determine which features learned by the neural network are significant, as well as the adaptation of the model for 3D images, or even 2 and 3D videos. Overall, the research and design process, and its results, demonstrated the immense potential in the use of neural networks for image quality assessment. I think that there are many projects that could make use of the concepts outlined in this paper, especially in fields such as augmented or virtual reality, or in video game design. I think that an analysis of image or video distortion and its impact on the user of a virtual reality headset, or the player of a video game, could be quite significant, since in a lot of instances there is a trade-off between operating efficiency and graphical quality. As this paper demonstrated, there are many portions of visible media that the human eye does not look at closely enough to notice distortions, and this could allow for a noticeable performance increase if a game or set designer were to reduce the distortion filtering on specific areas of the display. Alternately, the models proposed within this paper could be extended for use in the development of immersive media, as a quality benchmark which could be used as a development guideline. I think it would be quite interesting to develop and implement a model capable of performing a live analysis of image quality based on frames taken during a virtual reality experience, since this would show which areas of existing state-of-the-art VR technology can be further developed for greater immersion. This could help with areas of VR development, such as simulation sickness and the requirement for suspension of disbelief, bringing that technology closer to fooling the user's senses. Outside of these examples, there are many other uses for the technology outlined in this paper, any of which would make for an interesting and significant course project. While the use of image quality analysis for the development and improvement of a specific technology is one important application of the presented research, another project that would be both timely and valuable would investigate optimizations for the given models to improve the overall efficiency of models in the field. As proven by several experiments, the proposed approaches are some of the most efficient at image quality analysis, meaning that further refining them could lead to advances pushing the bounds of this area of study. Addressing the limitations mentioned by the author, and either adding constant variables or introducing dynamicity to the model, would help augment the model's computational efficiency or output accuracy, and potentially help determine significant values or ratios usable in alternate models. As an example, replacing the existing saliency model within the proposed methodologies with one more consistent with the human visual system could lead to a distinct increase in performance metrics from the weighted average approach, since it would allow for a more accurate representation in the saliency model. Currently, the most common approach to building a saliency model is using mean squared error and the peak signal-to-noise ratio, but it has been proven that this is not quite consistent with the human visual system, which is highly reliant on structure recognition. A saliency map that takes into account a specific pattern of fixations from eye tracking data could provide a much more realistic model of natural perception. Alternately, modifying the parameterization of an image during the feature extraction and fusion processes could also vastly increase the model's performance. Rather than training the model by providing it with 5.2 million parametric inputs, experimentation could be used to determine the most relevant parameters, the ones with the highest degree of influence on the model's outputs, as well as those most consistent with an accurate output, and extract those parameters alone, vastly simplifying the extraction step and minimizing the amount of work required in the regression and convolution models. Another highly beneficial project would be one of the author's suggested areas of future work, the use of image quality assessment for 3D images and video, or more significantly, for applications leveraging such technologies. The ability to create a more realistic, immersive viewing experience through the use of depth moderation is a trend that has seen a lot of public attention lately, since innovations like 3D TV, or the ability to observe an event such as a basketball game from thousands of cameras through a free viewpoint TV, would be industry-changing. One challenge facing the implementation of such tools is the creation of new types and degrees of distortions, caused by depth irregularities, dynamic viewpoints, image concatenation, and many other factors. The implementation of image quality assessment as part of a generative adversarial network could revolutionize the process of enhancing image quality, since the network would continuously strive for better results. And using the models proposed in this paper, such a model could be trained to ignore distortions in insignificant portions of the image, such as areas outside of the basketball court in the free viewpoint example, thereby reducing the computational load required to generate a clear image.